All right. So thanks for coming to my talk. I couldn't wait to break this silence. It was too embarrassing. So thanks for coming to my talk. Welcome. Today I'm going to be talking to you about how ransomware, in my opinion, has become a big change. Why it has made such a big change. And I'm going to be using the mobile use case because it's not commonly spoken about. But most of the methodologies that I'm going to present are applicable as well in the non-mobile cases. Shortly about myself, I recently joined Trend Micro's FTR research team, where we focus on various research topics. We try to, we do our best to predict what will be the future, a couple of years horizon, what are the future threats and risks. And also we do lots of investigation on crime cases with law enforcement. Before joining Trend, 6 months ago, I was an assistant professor in academia. I was working for Politecnico di Milano. Partially this work started there, and then I continued over at Trend Micro. I published some papers during my career. I was invited here and there to give talks about them. And I supervised a few students, and some of which I'm happily seeing here in the audience. I'm in the PC/review board of various conferences and workshops around the world, among which I would like to highlight the following ones. ACSAC is coming up next month in Hollywood. It's a very good agenda. Asia CCS, we just extended the deadline of a couple of weeks. So if you happen to have some cool research work, please submit there. And then DIMBA this year and previous year, OS, WebSec, Europe, and Eurosec. All right, so speaking about the content of this talk, I'm going to be starting giving you a brief retrospective view of ransomware, how we came up talking about mobile ransomware. And then I will give you 3-4 use cases, real use cases on a few families that are representative of the most interesting features of mobile ransomware and ransomware in general. And then I will tell you how we can use a static analysis approach to detect those features in order to process a large pool of applications and determine whether which of them are ransomware or not. And then I will conclude by presenting and releasing our tool, which implements all of these features. And then we'll draw my conclusion on an economics perspective on ransomware. This is a purely personal one. All right, so how we came about talking about mobile ransomware. We started from cryptovirology, a term that appeared about 20 years ago. This is a screenshot from a paper submitted at Oakland or IEEE Security and Privacy Symposium, where the authors defined the concept of cryptovirology as the use of cryptography with malicious purposes to mount extortion-based attacks. Think of this as 20 years ago. There was almost no notion of malware, right, as we have it today. So I found it quite fascinating. What I found even more fascinating is the fact that the authors have kind of predicted the role that electronic currency would have played in ransomware. They say that this could translate directly into the loss of US dollars if electronic money is implemented. Still thinking about 20 years ago. A specialized cryptovirus could be designed to search for e-money nodes and encrypt them, effectively hold the money as ransom. This is kind of what happened, right? It's slightly different. I mean, we're not using electronic currency as the subject of ransomware, but we're using electronic currency to pay for ransomware. So this is kind of fascinating to find something like this with such an advanced time. So if we fast forward to today, about 15 years ago, we start what we all know. We start seeing CryptoLocker and all the following families, which turned into a millionary business for the bad guys. There were a couple of isolated cases in 2000, 2004, of a couple of families that didn't really made any outbreak, few infections, and that was it. But then things started to get very serious from 2013, 2012. And this is where we introduced the little world, not so little in my opinion, of mobile ransomware. In 2014, 2015, I've started to notice a few families coming up specialized on doing malicious encryption for Android applications. And as you can see here, from the number of families, you can see that there is quite a lot of activities in the development of mobile ransomware. I also looked into the data that I have at our disposal in Trend, and I found out that between 2015 and 2016, there was a more than one order of magnitude increase in the number of ransomware samples submitted to our systems. Those kind of interesting to notice. And in certain areas, such as Australia, Singapore, and other countries, depending on the client basis, of course, there are a good fraction of ransomware as part of the whole pool of mobile malware. So this is quite interesting to me. All right, so now that we have kind of settled for the motivation of this work, I'm going to give you a few concrete use cases on how mobile ransomware works in practice. All right, so I'm going to be starting with the SLocker family, or also called SimpleLocker, which was one of the first ones that appeared. And it actually is specialized in screen locking. We found a few samples doing encryption, but they were isolated cases. If you think that we've analyzed a few tens of thousands of them, and we only found encryption in 50 of them. There is then the variant that appeared last year, which actually uses serious encryption using per device key. So, and then as a curious fact, it uses Tor or SMSs for CNC communication with the backend. But as I said, SLocker is famous because of it's one of the first cases of screen locking applications for Android. The technique that it uses, I call it soft button event hijacking. And the way it works is, if you're a little familiar with Android, you know that if you want to if you want to handle the event that originates from the pressure of any of these buttons, you know that you have to use an activity and override one of these methods, such as the on key down and the respective one on key up. So when you press and release a button, that function gets called, and if your activity overrides any of these methods, you can do your processing, right? So it's kind of an innocent-looking method, but effectively, the return value determines what happens next after the pressure of the button. So as you can see from the documentation here, you see, if you handle the event, return true. If you want to allow the event to be handled further, return false. This means that if you return true, you are effectively preventing any other handling of this event. So it means that if you do keep the view as it is, as an effect of pressing a button, and then you return true, any other activity following up on this event will never get that event. So you're actually actively manning the middling and denial of servicing the display of your phone, right? The other family I wanted to talk to you about is the caller, which is famous for its threatening text, in the sense that, as you know, that in a ransomware malware, you have to have, in addition to locking or encryption, you need to have some threatening text. So the text displayed to kind of convince you that your device is being held for ransom. And caller is a good representative example, because we have seen lots of effort in the development of around the text. So the text has been localized in 60 languages, if not more. And beyond that, there were even a very good effort that the developer has put into localizing not only the text, but also the key, the key people and the key terminology to refer to law enforcement locally for each country. So if you can find your country, you'll find some familiar faces or familiar logos. I think this is quite an impressive effort for a mobile malware. So here you can see an example of a threatening text. You might have seen something similar before. I highlight some of the key terms. You see that the malicious guy is trying to convince the victim that the phone has been blocked because it has been seen using or accessing prohibited content, that it has violated some articles of some criminal law in this case, etc., etc. So this is kind of the classic locking screen. Third family that I wanted to talk to you about because of its data encryption capability is the SVPang family, which started as a banking Trojan after stealing about $1 million of US dollars in frauds. The developer decided to switch to another kind of business and turned it into a ransomware family. So it has it's all victim user base, and decided to turn into ransomware. So it's famous because of its encryption capability. It uses real encryption, not as we have seen before, and it does screen locking using a new technique that hasn't been that we haven't seen before that. It's the abuse of the device administration API. I'll show you an example. So for the encryption, here there's the disassembled significant part of the code. You can see that it instantiates a cipher object, and then it uses that here at the bottom to perform an output to write on an output stream. That means that it's writing on the file to write the encrypted content. Right? This is a kind of a typical use of encryption in Android applications. Speaking of the device admin API abuse, as I told you, it can be used to, for example, lock the device. Here is what you see if you open an application that is doing for legitimate or non-legitimate purposes, we don't know, if it's doing device administration. So in the manifest, you will see at least one receiver asking for this permission to bind device admin, and this receiver will be entitled to do all the device administration stuff, like locking the device, wiping the device. It's used for remote wiping. If you're running a pool of devices in a company, you want to remote wipe them for security reasons. That's the legitimate use case. But of course, it can be used also in a malicious purpose, and that's the case of one of the latest family, September 2016, called LockDroid, which uses the reset password API, which is part of the device administration API, passing a pseudo-random passcode. So it generates a pseudo-random passcode, sends it to the CNC so that the bad guy knows it, and then it calls the lock now. That is, press the power buttons in some sense. So in this case, now the phone is completely locked, and you're locked out because the system has changed the password without your intervention. Fortunately, Google put a patch in a very prompt way, I have to say. In the upcoming version of Android Nougat, you cannot do this anymore. So there is no they even eliminated the legitimate use case. You're not able to invoke the reset password only more than once. So if you call it once to set the password, or if the user has set the password for once, if you call it another time, it will raise a security exception. So this, of course, breaks entirely the backward compatibility. You won't be able to administrate a device by changing its password remotely, which kind of, I like it, right? But it breaks completely some benign use cases for that. And it also prevents ransomware from doing this. Great. So now that we have kind of overviewed all the four main techniques for implementing the typical features of a ransomware application, we're going to see how we can detect them one after another. So ideally, this is what we would like to come up with, right? We have our malware analysis pipeline. We have as input a few APKs a day, and then we want to pass through a few of some of these detectors to say whether or not we found a threatening text, if we found a device locking implementation, if we found the usage of data encryption, or the abuse of the administration API. And then, based on the outputs of this, we can determine whether it's ransomware, whether it's simply scareware. For example, if it's only locking the device and displaying some threatening text, it's probably simple scareware, right? And if none of these features are detected, then it's probably only other malware or non-ransomware, generally. So starting with the threatening text detection, I hope that, from the example that I showed you, we can conclude that the text that we see that the bad guys are displaying must be clear and somewhat convincing. Otherwise, they will simply lose a victim, right? So the victim is not supposed to be an expert on Android. So what you want to have, as from the bad guy's perspective, is something very direct and simple and clean to understand. It's a completely different setting than spam, if you want. So you cannot introduce too many grammar errors. You cannot introduce strange fonts, right, to escape detection. So in addition to that, we have seen also the use of several coercion techniques. We have seen like accusations, referring to law codes and things like this. And of course, you want to have detailed payment instructions. This is key for implementing a good locking screen, right? You want your victim to easily find a way to pay. Otherwise, the victim might just be confused, bring the phone to the repair shop, and maybe the repair guy issues a reset. All the data is lost, but also the victim is lost from the perspective of the bad guy. So to analyze this text, we use a natural language processing plus a machine learning pipeline. And we start by extracting the text that we want to analyze. We have mainly three sources of text. First, we found that many families simply embed the text in plain text into the string variables or into XML resource files. And in this case, we simply disassemble the APK and we extract all the ASCII strings that we could find. In other cases, when we don't find anything with this technique, we simply run the sample in a sandbox for a few minutes, and then from the network trace, we decode what we can decode, or we get directly on the APIs and we take out all the strings that we could find there. And if this, in the case even this fails, we have the last resort technique. That is, we take a few screenshots during the execution and then we OCR them for text. Great. So now we have a blob of text that we want to determine whether it is threatening or not. This also applies to non-mobile ransomware. This applies in general, even to email filtering if you want. So the first thing that we do is we perform a simple language detection. So we determine if it's French, English, or whatever. And that is key because we need to apply several other techniques that are language dependent. For example, segmentation, that is splitting text into sentences, is language dependent. Stop word removal, that is removing non-interesting words, is also language dependent. Right? There are dictionaries of stop words out there. Stemming is also language dependent. Stemming means that we reduce every word to its basic form, such as locked becomes lock, safety becomes safe, etc., etc. So at the end of the day, we have a vector that encodes the presence or the absence of the words that we have analyzed so far. And this creates our training set. For each application that we analyze, we have a vector that encodes the content of the text in terms of words that are there and not there. The training set, we actually partitioned it, we actually label it. So this is the first part of our custom machine learning part. That is, we have taken a few representative samples and we categorize the text into money-related, law-related, accusation-related. There are other categories, but for the sake of displaying here, I'm only showing 3. But we have several categories that we look for. So now we can query this lightweight machine learning classifier, which is not yet a classifier, asking which is the best category for this sentence or for this group of sentences, right? And we go on a word-by-word basis, and then we average the results. Here is the scoring function. I don't want to go into the details. It's simply a maximization of the similarity, right? So as of now, we know which is the best category, and we know how close we are to a query, how close we are to that category. So in order to take a decision whether which is the best category, we use a series of thresholds that we set by setting a limit based on on known ransomware samples, so on text appearing in known ransomware samples. And on the other hand, we don't want to confuse this text with goodware text appearing, for example, in books or a corpus of text that is not related to ransomware. So we took two corpus of text, one from ransomware and one from non-ransomware, and we set this threshold in order to be able to separate. So now we can use this classifier effectively and ask, is this phrase best scored, best represented by the term money, by the category money? Yes, then probably it's likely to be ransomware. Is the best score in accusation or law, but not money? Then it's probably scareware. So we can use this in a custom way. You can use your custom categories and use this lightweight technique to determine the category of each of your text. Great. So we're now done for the threatening text detection. Let's move to the device locking mechanism. How do we detect whether the device is performing screen locking? So we have two broad techniques here. I told you before about the hijacking of the on key up, on key down soft keys. We also have other techniques that are, you can create a dialog and set that dialog to be non-cancelable. That's another option, which essentially makes the dialog non-escapable. But that's not super common. So we have implemented a detector for this, but we haven't found it in many samples. What we found in the majority of samples is the abuse of the key hijacking capabilities. And then the second broad category, as I told you before, is the device administration API abuse. But fortunately, we have an upcoming fix in Android N. So speaking of the first technique, what we want to find out is if there is any activity in the application that overrides these two methods, each of one. So if we have detected that, we go into the method that overrides this API method, and we execute all the statements. We have created a custom Smali simulator. Smali is the representation of the bytecode in a readable form. And we execute all the statements one by one. You can think of it as an assembly for Dalvik, right? So we execute all of them into the scope of these functions, and we follow function calls if there are any. And what we want to find out are two key elements. First, we want to find out if the input value, that is the variable that encodes the key that has been pressed, we want to find out if this key variable holds one of the target values. So we find out if, for example, it's receiving any value in the scope of 3 or 4. And to do that, we look for conditions. You can see here there is a register who is holding the value 4, and then this is compared with the first argument being passed to the function. This means that this guy here is trying to compare if the target key is actually, in this case, was the back key. So when the back key is escaped, this function does something. On the other hand, we want to find out all the output values. I told you before, the interesting case is when a return value equal true is returned. If that is the case, then it means that the view will be unescapable. So if there is a path, a code path, that goes into checking whether one of the target buttons has been pressed, and then returning 1, then it means that this method is simply doing denial of service of the whole event chain. Awesome. So now we know how to detect device locking. I'm sorry. Let's move to, I'm going to skip encryption for a second. I want to move to the second most important device locking mechanism, that is admin API abuse. Because we have seen it abused also in other families of malware outside ransomware. It's gaining a lot of popularity. So as I anticipated, we need to find if the manifest defines a receiver which asks for the bind device admin. Oops, I'm sorry. And if that is the case, we also need to check whether there is a separate file. In this case, is the device admin sample XML file, which is defining the policy that the application would like to comply to, would like to implement. In this case, the policies are, this is from the documentation, so it lists all the possible options. So some policies can implement, for example, password policies to limit the character set of passwords, or it can do resetting of password, forcing the lock, as I told you before, wiping the data, etc., etc. The one that I highlighted are the ones which are, of course, important for our detection case. So if we look at the code, for example, here I gave you the reference to the hash. If you want to reverse this sample, you will find out that at some point is calling the lock now function that is effectively locking out the device, as I told you before. Interesting, I also found that this sample is having an uninstallation feature that is remove active admin, which means that it's deinstalling its admin capabilities for releasing the device, essentially. Great. So starting from the manifest, we would like to find out whether any of these dangerous methods here specified by these policies are invoked. So what we do is we start from the receiver, and on the other hand, we have the control flow at hand. I use FlowDroid to create the CFG, which is quite efficient. And then we calculate all the entry points that we find in the CFG, and we visit the CFG to see if we find that at some point there is a call to one of these dangerous functions, the lock now, for example. So there are cases where nothing is found because some of these malware are obfuscated and also protected from reverse engineering, so they are using a lot of reflection. So we try to make an effort here to resolve the reflective calls. Reflective calls mean, for example, that instead of calling the method directly, so you wouldn't see a path in the CFG, you would see a virtual or dynamic path that is only known at execution time. So what we do is we try to find out if there are calls to the Java Reflection API, for example, the invoke, and then we try to find out if the method, if the string variable that is encoding the method name is somehow pointing to a known method that is also a node in the CFG graph. And in that case, we simply connect all the dots. So it's kind of a materializing part of the dynamic component of the CFG, right, at runtime. Sorry, at analysis time. So sometimes methods are, software protection are fairly good. So sometimes the method name are not straightforward. So believe me or not, this string is holding the obfuscated name open. So this sample here is trying to open the camera. You can guess why. And what we do here, in order to find out which is the method that is being called reflectively, we start from the bottom. We start from the invocation of the reflection API. We go back until we find the target object. In this case, the method object is the target one. We go back until we find the allocation of the variable that holds the obfuscated version of the method being called. And what we would like to do now is to be able to execute in place to find out what is the value of the deobfuscated object. But of course, we cannot do it because this will be known only at runtime. So what we do is actually we use the reflection API to our advantage to take all of these methods and to execute them. So we supply all the arguments that are known from the code, and we execute using the reflection API one step to another, from the definition of the variable, if we find it, up to the end of the flow, that is the invoke method call. So in this case, by this point of execution here, we would have known, we would know which is the target method because we have access to the content of the deobfuscated variable. So this doesn't work always, of course, but in most of the cases, it's pretty lightweight and it works fine. So now we are done with device admin API abuse, and I also gave you some hints on how we can better deobfuscate obfuscated methods. Now we want to conclude with data encryption. So we've examined a few hundreds of samples, and we have seen that at the end of the day, the encryption flow boils down to a loop that looks like this. So it accesses to a list of files, and there are several ways that an application can list files. For example, by accessing the external storage and then going through the file output by the list files function or the list function, or by using the runtime execution and simply running ls or something like this. And then from this point, one file after another, we see the allocation of the file input stream or equivalent. So we have a few target methods that we look for. And then at the end of the day, you see that the flow is ending into a cipher object that is performing the actual encryption. So generally, this problem can be solved with a data flow analysis. And in particular, we use taint analysis, where our interesting sources include, for example, the file listing methods, and the sink, which are the end of the flows, include methods such as cipher do final or cipher output stream. We have a long list of interesting and configurable flows. And of course, we need to have a way to determine that whether these flows are UI initiated or not. So for example, if there is an execution of this flow as a result of an event on the API, on the UI. So for instance, if there is a button that is being pressed, and as a result of that event, this flow is executed, that's not interesting for us, because that's something that is user initiated somehow. So we want to find if there are flows that are executed regardless of user intervention. Fortunately, all of these nice features are already implemented in FlowDroid, which also has the exclusion of the UI components from the flow analysis. And what we do is what I hinted you before. We track all the flows that originate from file listing operations and end up into Cipher, into the encryption API, essentially. We had to modify FlowDroid a little bit because FlowDroid doesn't propagate taint labels through byte to byte arrays. It's kind of a limitation of the tool. There is also the option of using implicit flows, but that makes the number of states, number of paths exploding very easily. So we kind of customize the tool a little bit to propagate taint information only in the few cases that end up into byte arrays and then into some buffer variables. Great. So now we have our pipelines completed. We know how to detect all of these features, at least in the cases that I've showed you before. The only problem is that it takes time. It takes a lot of time to run static analysis and flow analysis. If you have done it before, you know how expensive it could be. And by expensive, I mean 12 seconds on average, which looks pretty fast with respect to manual reverse engineering. But in certain cases, we would see samples timing out our analysis for going above 5 minutes. So depending on how the code is organized, this can take a lot. So if you want to run this at an app store scale kind of workload, this is not applicable, clearly. So we decided to adopt a pre-filtering approach. And we moved from this observation. We observed that the majority of applications that are out there are fortunately goodware, so non-interesting. We don't want to spend expensive analysis time on these applications. We would like to quickly filter them out and focus on the core, focus on the suspicious files that are maybe malware or, interesting for us, ransomware, right? So these are the design principles that we adopted. We want to have a very fast filter that is very good at detecting if we have a goodware, so very precise on solving one of the two problems, and it's perfectly okay if it makes some mistakes in the other direction. So it's fine if it says, oh, I think this is suspicious, but then in the end it turns out to be benign. It's not fine if it says, oh, I think this is benign, but at the end of the day is actually malicious. We don't want to make that mistake. We are okay making the mistake in the first place. So this translates to a machine learning technique called cost-sensitive classification. With cost-sensitive classification, you actually move the threshold, the decision threshold on one side of the problem. You want to train the classifier on the fact that the cost of a false positive is much higher than the cost of a false negative. So you're kind of biasing the classifier somehow. You're telling, hey, it is very costly to confuse a malicious as benign, much more costly than the opposite one. And we set a parameter of about 15 times in our experiments. And on top of these, below these, we use an ensemble of classifiers. We use 3 classifiers. We use a J48 decision tree, random forest, and decision tables, which are actually implementing the actual classification problem. And in order to take a decision, we use majority voting. That is, we take the most common answer among these 3. Speaking of features, from the malware analysis literature, the set of features to detect malware is fairly established, so we didn't want to reinvent the wheel. So we took inspiration from some of those features that have been proposed in the literature, and we also added a few novel ones. Of course, we are not solving, I want to stress that here we are not solving a malware detection problem. Here we are solving a goodware detection problem. So we are more focused on the precision on detecting goodware. We don't care about if we make a mistake on the opposite direction. So speaking of features more concretely, what we have in our classifiers are features that encode the presence or the absence of some permissions. We have file statistics such as number of files, number of permissions, number of services, size of the classes, number of packages, etc., etc. We also have some lightweight so-called behavioral features that encode the fact that some sensitive APIs are present in the code. So all these features together, if you take them together, they do a good job into detecting if an application is goodware. Of course, if you take them individually, they don't make a lot of sense. So it turns out that this choice of features and this choice of classification approach works fairly well. From our experiments on hundreds of thousands of benign and malware samples, the precision is fairly good. And it's also quite fast. You can see here we moved from 12 seconds on average to 1.25 seconds on average, which is about 1 order of magnitude. So here you can see we're also exposing this service as a web service. There are all the URL at the end of the presentation. As output, we give you the scoring that is the output of the classifiers, and also we give you the details on which features have been found in the sample. So you will be able to use this service publicly. So in addition to the experiments on the speed, we also did some experiments on the detection accuracy, of course, the detection capabilities of the whole pipeline, because that's the most interesting part. So we adopted 2 broad data sources. One data source was composed basically by malware and goodware. So we have a few hundred of thousands of samples in this bucket. And we use this for detecting how many false positives our instrument is finding. So we want this to be very low, of course. On the other hand, we have a set of selected ransomware. And when I say selected, I mean that we manually analyzed a few samples on this pool to make sure that they were actually doing ransomware. Because you know that if you go on VirusTotal and query for ScreenLocker or ransomware families in general, you might get some false positive. That's a common problem that all the practitioners and researchers are aware of. So we kind of did some random checking to see if we were actually targeting good samples. And then we have a continuously running experiment of which we don't have any ground truth. That is, we take the daily feed of the top, top 100, top 500 probably samples from VirusTotal, querying from key family names. And so far we have analyzed something like some tens of thousands of samples. The results are pretty satisfactory. I'm very happy with the false positives. There are a few corner cases that include, for instance, applications that have large portion of text that is referring to copyright or law-related terms. That was kind of expected. We probably have to bias a little bit the decision on the other features for if this happens. So we were thinking of removing these after an output that says, okay, I think it's ransomware mostly related on the contribution of the text analysis. Probably we should remove the text analysis component, rerun the analysis, and see if the result changes or not, right? And then we also found 6 cases of benign applications that were using on-key up and on-key down the mechanism to customize the user experience, and also that was kind of expected. But on a basis of a few hundred of thousands of samples, that's pretty encouraging. Speaking of the detection rate, that's also quite encouraging. If we take out the 49 samples that we found to be mislabeled, so we took all the false negatives here, and we analyzed them manually to see if they had actually malicious functionalities implemented, and we couldn't find them. So we concluded that they were mislabeled by some of the vendors. The interesting case that we found were 11 applications, but that were not detected because the language was unsupported, in the sense that our classifier didn't have the information on the training on Spanish and Russian, right? So we say, okay, we could simply take these samples, take the text found on this sample, and then use it to train the classifier. But that would be cheating, because we have a query here that we want to run, and we want to see if the classifier is able to classify them without showing them the sample first. Otherwise, it's complete cheating. So what we did is, since we didn't have any other samples localized in Spanish and Russian, we took the samples that we had localized in English, and we use an automated translator such as Google Translate to translate the sentences into the best approximation of Spanish and Russian, right? So this was great because it was completely automatic, right? And you can use it even to sort of anticipate the spread of one family into another country of which you haven't seen any evidence yet. So you don't need the actual sample to be able to detect the outbreak of a family in a country. What you need is a few sentences coming from other applications, localized in other languages. So that was a pretty happy incident. So as I said, we will be releasing the tool. In a few moments, I will be pushing the source code onto this repository. The service API is already opened. I think we opened it a year ago, probably less than a year ago. And it's available at this ransom.mobi address. We use it, as I told you before, to analyze a daily feed coming from VirusTotal. So we query VirusTotal, and whatever we find containing significant labels, we analyze it. From this URL, which is not public in the main page, so you want to take note of it. I mean, it's not very creative in the name, but you couldn't find it in any other source. You will find the detailed analysis of each sample that we find. So we try to divide it by family. Of course, there's going to be some overlapping because of the well-known labeling problem. We show some statistics on the language. We show some statistics on which families have, how many times in a certain family we see the detection of lock techniques. If we see the text, the threatening text, and which is the language, and other details, other aggregated details. If you click on a family name at the top here, you can go down in the details. You will see all the samples being analyzed. You can download the analysis result as a JSON file. You'll also be able to download the sample, but for that you need a password. So you can write me an email if you need access to those samples. You can also search. You can also order the columns. You can filter the columns. So we try to make it at least usable from a human. And here is the output of the detection only for the ransomware part, right? I showed you before the pre-filtering. This is not including the pre-filtering. This is only including the output of the detection. of the ransomware detection part. So speaking of the details, we published a couple of papers, one last year at RAID 2015 in Japan, and one has been published this year, has been just presented in China by my student. And you can find the PDFs describing all the implementation details on my webpage here, or on my GitHub repo. You'll find all the papers. You'll also find the slides. I'll be publishing the slides on this repo as well. So in the first paper, we kind of set the overall idea. And in the second paper, we presented the pre-filtering plus the reflection enhancement that I discussed before. I'm sorry. All right, so I promised, in the title of the presentation, I promised that I would have given you my personal conclusion of why ransomware from an economical perspective is so different. Actually, in general, it's different, but I like it to give also a spin on economics, even though I'm not an expert in economics, so beware of what I'm saying. If there is anyone who is expert in economics, please come talk to me. I spoke with some of my friends, and they say, yeah, what I said, it kind of makes sense. So I said, well, I will include it in my presentation. So we ran, Trend was kind enough to run a survey in the UK among about 300 companies having in the tech manufacturing business, having about 1,000 employees, so not so small, not so large companies. And they were asked what was their posture on ransomware infections. So those who weren't infected, they were asked, what would you do in case of a ransomware infection? And those who were infected were asked, what did you do once you knew that you were infected, and how it turned out, how it worked out from a data recovery perspective. So the first question, before infection, people are bullish. They say, oh, I would never pay. The majority of them, they say, of course I will never pay. But then if you ask the people who were hit by ransomware, the majority of them would pay, right? More than 50% of them would pay. So you can see here how ransomware, once you experience it, it changes everything. It can even change your posture. Speaking of recovery, there is a good percentage of recovery rate. There were cases of companies not being able to restore the data because the bad guys simply ran away with a bunch of bitcoins. But I call that as an unfortunate incident, because most of the bad guys are actually good guys in this perspective. From this perspective, what they do is simply we have a very low barrier at the entrance, so it is very easy to get into the ransomware business, but it is also very easy to screw it up, because if you want to run a backend to keep track of all the private key and all the release of the private keys, it's kind of complicated. So I think that these 35% are cases of simply inexperienced attackers, so to speak. So we can, at least I hope I convinced some of you that we can agree on these points. Why ransomware is different is, first of all, because it changes everything. Like, it changed completely the approach to an incident response case. It is completely destructive, which if you think about malware 20 years ago or 10 years ago, but even 5 years ago, we didn't know that a malware could simply come and break everything. We were used to botnet kind of malware, which was all but noisy, was completely stealthy, because the objective of that malware was to keep control of the device under the hood without showing off. On the opposite side, malware has to show up. It is the main purpose of ransomware has to show up. It is the main purpose of ransomware to show up and say, hey, I'm holding your device as ransom. You have to pay. If that doesn't occur, if that noisy behavior doesn't show up, then the ransomware has completely failed, right? And the business model doesn't work. So no show, no gold. Second, it is a pure profit kind of business. There is a link here to an analysis done by the Data Gravity guys, and they estimated that last year the whole ransomware market was more profitable than 68.7% of the companies in the Forbes 2000 in the top Forbes 2000, which is kind of remarkable. But if you think about, you don't need a lot of cost, direct cost to run ransomware. You need technical expertise, but once you set it, you can amortize that investment very easily. So it's mostly profit business. And third, even if we have seen some cases of bad attackers, it's a business model that is backed by honesty, right? The bad guys have to be honest in the majority of cases, otherwise their dishonesty will ruin the business. So the more the bad guys are honest, the more the business model works better. So these three characteristics have created a sort of a vicious circle, if you want. The more the victims pay, the more the attackers' expectation increase, and they gain more confidence in the fact that their business model works well. And so they increase the prices. We have seen cases of prices getting higher and higher and higher, but also cases of prices customized on a per victim basis. There was one case, I think, in a hospital where the victim paid almost immediately, agreed to pay almost immediately, and the bad guy say, oh, you know what, I doubled the price, because it means that you can afford it. So if you can afford 10,000, you can afford 20,000 easily, right? And that happened. So you can see from this center of the vicious circle that there is a key advantage here that the attackers are kind of exploiting. And if we want to reverse the way of the vicious circle, we will have to exploit it too. The key advantage here is how much can the victim afford. This is becoming a key information for the attackers to succeed into making a very explosive business compared to a mass kind of attacks where you ask for $300 or $500 to every victim, right? Unfortunately, I've seen cases of vendors acting in favor of the bad guys, if you want. I'm quoting something that I found on a website of a vendor that says, we will reimburse up to $1,000 per endpoint. This is saying it out loud on the website. Or $1 million in ransomware protection overall for the company, guaranteed. So this vendor is kind of backing their technology with an insurance, which it's kind of fine. I can understand it as an agreement between me and the client. I would like to offer some extra layer of protection, but I don't like the fact that this is being made public and out loud to the whole world, because this is what the attackers have been waiting for, knowing how much the customers of this vendor can afford, right? And they make it even worse, I think. They say it's time for security companies to back their technology and provide users with the financial assurance that they deserve against ransomware attack. So they're making it sound like a wake-up call. Like, hey, vendors, we should all do this. Well, my wake-up call for this vendor and other vendors that are probably thinking about going into this direction is to try to think for a moment, seriously, what could be the long-term effect if this is adopted on a wide scale. So think of how the money flows in the ransomware business, and think how much this can act as an amplifier of these vicious circles. Thank you.